This is lecture 20 on urban transportation planning. We will discuss on trip distribution analysis in this class, which is the third major step in the 4-step planning process. At the end of the first step, namely trip generation analysis, we obtained this result. We considered zone centroids as points of origins and destinations for all the trips, and then we obtained the trip ends associated with each of the traffic zones as percent trip ends without identifying the mode used by individuals. We just obtained percent trip ends in total associated with each of the traffic zones at the end of step 1, namely trip generation analysis, which includes both trip production as well as trip attraction analysis, right. In step 2, namely mode choice analysis or modal split analysis, what we did is this: we tried to assign modes for these trip ends. We tried to find out how many of these trip ends will be associated with the mode foot, how many will be associated with the mode motorized two-wheeler, how many will be associated with another mode, say bicycle, and so on. That is what we did. In that process, we found that disaggregate mode choice model, which considers each individual as separate entity for the purpose of mode choice analysis, is more appropriate, because other methodologies assume average behavior of travelers at zonal level, which may not accurately replicate the reality. Then we also assumed that utility of alternative modes cannot be treated as a constant quantity, because the perception of utility of modes varies from individual to individual. So we treated utility as the random quantity and considered each and every individual as independent entity for the purpose of mode choice analysis. Based on these two aspects, we found that logit model of mode choice is the right analytical procedure which can provide appropriate result for mode choice analysis. And we have also seen a set of case studies in the application of logit model of mode choice, isn't it? And at the end of mode choice analysis, this is what we will get. These white lines will assume different shades with different proportions. Each color pertains to a particular mode of travel. This is what we essentially did at the end of mode choice analysis. You can see we have indicated white colored ones as trips made by foot, yellow colored ones trips made by two-wheeler, and red ones trips made by car, blue one motorized three-wheeler, and then the other one by IPT, then trips made by bicycle, train, and bus. These were the different alternative modes that we discussed under Indian conditions. So this is what we do at the end of mode choice analysis. Still we are dealing with trip ends only, which are zone based. The only difference we have made is that we have associated modes for the trip ends. Otherwise data still is zone based, and these are all percent trips, not vehicular trips, percent trips with identification of the modes used for the trips. That is it, right. With this background, let us proceed with the next step, and let us also identify in the master flow chart where exactly we are now when we start our third step of the analysis. We have completed, as you can recall, trip generation models, captive modal split model, choice model split models. These 3 boxes are completed now. We are into the 4th box, namely trip distribution modeling exercise. And trip distribution is aimed at developing a procedure that synthesizes the trip linkages between traffic zones for both transit captive and choice trip makers. Please recall, when we started mode choice analysis, we segregated transit captive riders and did the analysis only for choice riders. When we do the 3rd step, we put both the categories of travelers together and do the analysis for both the groups, both for transit captive as well as choice riders. All the trips are to be distributed. And the distribution of trips between zones can be better illustrated in the form of a matrix. Why in the form of a matrix? Because we are going to study distribution of trips from one zone to all the other zones. If there are 100 zones in an urban area, we are going to study how the trips or trip ends at zone 1 are going to get distributed to all the other zones including zone 1. There could be trips distributed within the zone also. So it is, when you consider zone by zone, it becomes 100 by 100 analysis. So that way it will be easy for us to present trip distribution data in the form of a matrix. That is the idea. And there are 2 types of trip distribution matrices. The first one is production attraction, PA matrix, because as you may recall, any traffic zone will produce trips or attract trips, or simultaneously there will be productions as well as attractions in a particular traffic zone. So when you develop a matrix, it is going to be production attraction matrix. But please remember, later on when you get into step 4 for traffic assignment, we need to know the direction of movement also, the exact origin and destination. To give input for route assignment analysis, we may have to prepare another matrix named OD matrix, origin destination matrix. This OD matrix can be prepared based on PA matrix, production attraction matrix. So we can say here there are 2 types of matrices. Number 1, production attraction or PA matrix. Number 2, origin destination or OD matrix. Clear? Let us first take production attraction matrix and see how this matrix is prepared and how we understand the data set given in a PA matrix. This is the PA matrix. We are taking production zones along the row in the table and attraction zones along the column. Production zones along rows and attraction zones along columns. I have just indicated the number of zones as 1, 2, etc. up to n, both along the row as well as along the column. And the cell values in the matrix gives a particular information to us. The cell value Tij means what? This cell value will give the number of trips produced at zone I and attracted to zone J. That number will be given in this cell. T1J, for example, will give us information about number of trips produced at zone 1 and attracted to zone J, right. And if you sum up all the cell values along a row, what will be the result? The sum should give us, for example, if we take zone 1, the first cell value gives T11 trips produced at 1 and attracted to 1 itself. Then we will have 1, 2, 1, 3 and so on up to 1n, right. That means the distribution pattern pertaining to zone 1 is given along one row. So if you sum up all the cell values, you must get the total of the trip production of that particular zone, isn't it, because we just distribute the total trip production between the zone under consideration and all other zones. So obviously when you add up all the cell values along a row, you need to get the total trip production of that particular zone, right. Similarly, if you sum all the cell values along a column, add up all the cell values along a column, let us say T11, 1, 2 and so on and N1, right. We have indicated that value as A1, that is nothing but the total of the trips attracted by zone 1. The sequence will be like this: 1, 1, then what will be the cell value here? This is produced in 1, attracted to 1, here it will be produced in 2, attracted to 1, produced in 3, attracted to 1, right. All these things are trips attracted to 1, right. Say last value is produced in n attracted to 1. So that is how the column total should give you the total trip attraction in a particular traffic zone, right. So this is a presentation of the trip attraction distribution data in the matrix form is very helpful. To summarize the same thing, we can say the cell element Tij means the number of trips produced at zone I and attracted to zone J. Hence a PA matrix has no directional meaning and its cell elements represent trip interchanges only. This is a very important statement. You cannot find out the direction of movement by looking at a PA matrix. It just gives you information about total number of trip interchanges between zonal pairs. There is no information provided with regard to the direction of movement. So this has to be understood very clearly, and the number of production zones generally equals the number of attraction zones in practice. The row sum Pi is the total number of trips produced at zone I as we understood, and the column sum Aj is the total number of trips attracted to zone J, isn't it. The sum of productions T equals the sum of attractions. Finally we found that sum of the sums along the row and column should also be equal, because anyway total number of trips produced should have got attracted somewhere within the study area. Normally both are equal. Then the OD matrix. As I said, OD matrix is necessary to have information about the direction of movement, origin and destination. Once you have this information, you can perceive the direction of movement of trips from one zone to all other zones. That is the purpose of preparing a OD matrix. Now here the destination zones are given along columns and origin zones are given along rows. That is the only difference between PA matrix and OD matrix. and in the notation there is a minor difference. Earlier we named the cell value as Tij for example. In this case it is named as Ti-j to differentiate between PA matrix and OD matrix. Ti-j means trips originating from I destined to j, that is the meaning. The number in that cell will give you information about the number of trips originating from I and destined to j, right. That means the direction of movement is clearly indicated, that is the point. And T1-1 means number of trips originating from 1 destined to 1 itself, intrazonal trips. T1-2 number of trips originating at 1 destined to 2, they are interzonal trips. You may wonder, why should we bother about intrazonal trips? Are we really interested in intrazonal trips? Because right from beginning we understood trip as a movement between zone centroids. We never discussed about movements within a traffic zone, isn't it? So in this case also, for completion's sake, we have information about intrazonal trips. For subsequent analysis also we will consider only interzonal trips, otherwise we will be deviating from the earlier assumption of defining trip as a movement between zone centroids. Okay. It may not have any drawback because, as I said earlier, zones are small urban areas and there is no need to worry about the road network within a smaller area. Our concern is the major roads developed or existing in an urban area, right. If you sum up the cell values along a row for a particular zone, what will be the result? It will give information about what? Let us say you are adding T1-1, T1-2, 1-j, 1-n along this row, and it is indicated as O1. The row sum is indicated as O1. O1 means what?
Total trips originating from the zone 1.
Total number of trips originating from zone 1, that is it. Similarly, the column totals will give information about total of the trips destined to a particular zone. You can clearly see here, if you consider zone 1, it is going to be 1-1, then it will be 2-1, 3-1 and so on, n-1. So all pertaining to one zone. So D1 obviously gives information about total of the trips, okay, destined to zone 1, isn't it? And the cell element denoted by Ti-j is the number of trips originating from I and destined to j, as we understood earlier, and therefore an OD matrix has directional meaning. It gives you information about direction of movement and its cell elements represent trip flows. Actually, you will have a feel of the trip flow from one zone centroid to another zone centroid. The row sum OI is the total number of trips originating from zone I, and column sum Dj is the total number of trips destined to zone j. This is our concern, how to convert a PA matrix into a OD matrix. Initially we would have estimated the total trip production and attraction zone wise. That information is available to us through step 1. and step 2 we have done the mode choice analysis. Now while presenting the data in the form of PA matrix we have no problem, because we have information in terms of P and A, production and attraction, but we need to have OD information for route assignment. So in this context it is better to understand how to convert a PA matrix into a OD matrix. It is not difficult, it is very simple. For directional traffic assignment, as I said, the PA matrix must be converted to an OD matrix. Let us consider a very small example, trip interchange between zones 1 and 2 as shown in the following figure. Let us say this is the production attraction information, PA information. Zone 1 is a production zone, zone 2 is an attraction zone, and the total number of trip interchanges between these two zones is 200 trips are interchanged between zones 1 and 2. We have no information about the direction of movement. PA matrix will not give you the directional information, right. Let us say the proportion of trips originating from the production zone denoted by the letter lambda be 0.4. Let us say 40% of the trips of the production zone are originating from that zone, right, arrows tending outwards, and 60% destined to that zone obviously. Once you have this information, then put in this information here to get OD information. Then I can say that number of trips originating from 1 and destined to 2 is 0.4 into 200, which is 80 trips, is not it. 80 trips are originating from 1 and destined to 2, and then obviously the number of trips originating from 2 destined to 1 is going to be 1 minus 0.4, that is 0.6 into 200, which is 120 trips are originating from 2 and destined to 1. So first we had information about the sum only, 120 plus 80. Now we are able to split by knowing the proportion of trips originating from a particular zone. So based on this principle we can just write a generalized formula for converting PA information into OD information. The general formulae for finding the cell elements of an OD matrix from the cell elements of PA matrix are as follows. You can say Ti dash j is equal to lambda times Tij plus 1 minus lambda times Tji, or in other words the number of trips originating from I destined to j is equal to the proportion of trips originating at I multiplied by the number giving information about trips produced at I and attracted to j, that is what is meant by Tij, plus 1 minus lambda times the number of trips produced at j and attracted to I, is not it. That is what we mean by this simple equation. And similarly you can write the other directional movement, namely Tj dash I, number of trips originating at j and destined to I, is equal to lambda times Tji plus 1 minus lambda times Tij, right. So, using these two equations you should be able to convert any cell value of a PA matrix into an equivalent cell value of OD matrix. So, given a matrix we should be able to apply this formula and convert the cell values, that is what we want, conversion of PA matrix into OD matrix. Is that clear? Let us take a very small numerical example to understand these two equations much better. Example of conversion of PA matrix into OD matrix, let us say lambda value given is 0.4, right. This is the PA matrix given to us, production, attraction. There are two traffic zones involved, right. T11 is 20, T12 is 100, T21 is 40, T22 is 60, and P1 is 120, P2 is 100, A1 is 60 and A2 is 160, is not it? That is information given to us. Let us say we are interested to convert the cell value pertaining to T11. What will be the value of T1-1? T11 means trips produced at zone 1 and attracted to zone 1 itself, right, and the corresponding cell value in OD matrix will be trips originating from 1 and destined to zone 1 itself. In that case what will be the cell value for this particular cell in OD matrix? Same, there will not be any change at all, whereas there will be a difference in respect of the other cell value 1 2, lambda is 0.4. Let us say we are interested to know the value of T1-2, T1-2. What do we do? Lambda times T12 plus 1 minus lambda times T21, is not it? So, that will give you the value for this particular cell in OD matrix. So, that is what I have done here. 20 remains unchanged and 100 becomes 64 here, cell value of 100 has become 64. How? It is 40 plus 24, 100 is Tij, lambda value is 0.4, 0.4 times 100 is 40, right, plus 1 minus lambda is 0.6 times T21, T21 is 40, 0.6 times 40 is 24. So, we get 64 as a cell value in OD matrix, and similarly you can get the values for other cells. Interestingly, you can see the diagonal cell values are unchanged because they represent intrazonal movements and they will remain unchanged, clear. So, you can apply the same principle to convert any size of PA matrix into OD matrix. And you may wonder whether lambda is going to be having a constant value or it may have different values and so on, isn't it? That is a very important question to be answered. What is the likely value of lambda in practice? You take a traffic zone, right. Let us say about certain number of trips are originating from the zone. People moving out of the zone are likely to come back most of the times, okay, and even if there is some deviation there could be some compensating error, there could be some one way movement outward, some one way movement inward also, and in general it has been observed that lambda is mostly 0.5 for most of the traffic zones in an urban area, okay. The movement, two way movements are almost balancing, and let us take lambda to be 0.5 and do the same exercise and check whether there is any major difference between this result and the result of the practical case of lambda being 0.5. Note that the sum Tij and Tji equals to sum Ti dash j and Tj dash I. Of course, that is obvious from the previous example. Also, the diagonal elements in both the matrices are the same, they remain unchanged, that is what we have seen. In practice, as I said, the value of lambda will be around 0.5 for a 24-hour matrix. We do normally 24-hour matrix, 1 day travel is our interest, which will result in a symmetrical OD matrix. That is the difference. The earlier case, the symmetry was not there. There were changes in the cell values of the matrix. If you look at the OD matrix, here it is 64, here 76, right, and let us see what happens to these cell values when we take lambda to be equal to 0.5. Consider the previous case with lambda to be equal to 0.5. This is the PA matrix and the OD matrix will be like this. You will have 70 and 70 for 1 2 and 2 1, cell values T 1 dash 2 and T 2 dash 1 because of the symmetry. That is the main difference between the previous case and this thing. This is what we come across mostly in practice. There could be, of course, I would like to caution you, we need not blindly assume that lambda is going to be only 0.5. There could be situations where you may have to deal with different lambda values. Since the general formula is known to us, there is no problem, we can always apply the formula and get the cell values while converting TA matrix into OD matrix. Clear? Please note that we have discussed so far about just the presentation of the data available to us, okay, and we have not started the process of trip distribution modeling. Now we need to study the process of modeling trip distribution. Any modeling process involves first a clear understanding of the causal variables. Can you just guess the possible factors that may influence distribution of trips between traffic zones? Unless we identify factors, we will not be able to develop a model, isn't it? We extract or derive variables from the identified factors and then formulate an analytical framework to model any process, isn't it? What are the factors that might influence distribution of trips between traffic zones? Land use type, okay. We have different types of land uses, and it is very difficult to say that distribution is influenced by land use. Distribution is two-way movement of trips between traffic zones, isn't it? For example, trips between zone 1 and zone 5 might be more compared to trips interchanged between zone 1 and zone 100, and we should be able to theoretically explain why it is different. That is what we mean by trip distribution modeling. Let us try to understand certain basic aspects of trip distribution. The rationale of trip distribution is as follows: all trip attracting zones J in the region or in the urban area are in competition with each other to attract trips produced by each zone I. This is the basis. We assume that all the traffic zones in the urban area are competing with one another to attract as many trips as possible from a particular zone I or from each of the other zones, right. There is a kind of competition to attract trips. Let us perceive that way first, and then everything else being equal, more trips will be attracted by zones that have higher level of attractiveness. It is obvious when they are competing for attracting more trips from trip producing zones, when the attractiveness of a particular zone is relatively high, that particular zone is likely to attract more trips from all other producing zones, is not it. Now our point or the objective should be to define the attractiveness of traffic zones, how to define the attractiveness, so that we will be able to quantify the same and then put that as a factor in the modeling process. And however, other intervening factors affect the choice of J as well. What are the other intervening factors? First, we have said that the zone which is relatively more attractive will be able to attract more trips, but it cannot be taken to be 100% correct. There are other intervening factors affecting the choice of J as well. We cannot say that J is going to be the zone which attracts more trips. What are the other possible factors? Let us say zone 100 is the most attractive zone as far as trip attraction is concerned. It is relatively an attractive zone compared to all other zones. Zone 50 is relatively less attractive, and we are trying to understand the distribution of trips between zone 1 and 50 and 1 and 100. Let us say zone number 100 is at 10 kilometers away from zone 1, zone 50 is just 5 kilometers away from zone 1, but zone 100 is more attractive compared to zone 50. What will be the trip distribution pattern? People have to travel long distance to reach zone 100 and lesser distance to reach zone 50. Even though zone 50 might be relatively less attractive, let us say shopping trips, more trips may be attracted from 1 to 50 than from 1 to 100 because of this intervening factor of travel distance, right. Now we are able to identify another factor to understand distribution of trips, namely intervening spatial separation between zones, is not it. Consider for example the case of two identical shopping centers of equal attractiveness, for example, competing for the shopping trips produced by a given zone I. There are two attraction zones with good shopping facility, both the zones are competing with one another to attract trips from zone I, right. If the distances between zones I and each of the two centers are different, shoppers residing in zone I will show a preference for the closer of the two identical centers. That is what I said, okay, right. Attractiveness is same, but distance makes a difference. Shoppers obviously prefer the one which is closer to them. That is how spatial separation comes into play in understanding distribution of trips. Thus, the intervening difficulty of travel between the producing zone I and each of the competing zones J has a definite effect on the choice of attraction zone, intervening factor. Now should we have to understand the intervening factor, namely spatial separation, in terms of distance or time or some other factor. Can we just take distance as a factor, intervening factor? If you take distance, it may or may not work well. Normally in urban travel, time of travel is understood better as the real effect of spatial separation than the actual distance, right. Distance may be less in a particular case, but travel time may be more because there may not be good road network available to connect these two zonal pairs, right. So travel time appears to be more attractive, but travel time may be less, but the available mode may be expensive compared to another choice where travel time is slightly more but cost of travel is less. Then people may perceive differently, after all they have to spend to make the trip. So you see the distance, travel time and cost of journey all work together simultaneously while choosing a destination point. So we have to think on these lines and take a decision to really define the intervening factor in terms of spatial separation related variables. Okay. The shopping center example, distance is cited as a measure of this difficulty of travel, but other measures of this effect may be used, such as travel time or some generalized cost that includes travel time, out of pocket cost and the like. Okay. You may not have to consider only distance or only travel time, you can have a combination of factors and put them all together and give some name for that and use that as a factor influencing trip distribution. And this factor is known as the travel impedance. The notation Wij is used to denote this generalized cost. So all these factors together is termed as generalized cost of travel, okay, which is also known as travel impedance. What do you understand by generalized cost? The aggregate money value of making a trip is called generalized cost. In one trip you may spend less time and more out of pocket cost, right, and you may enjoy a better comfort in travel. And if you assign money value for each of these elements including your travel time, you can get aggregate money value for that particular trip. In another case you may spend more time but spend less of out of pocket money, maybe you may be subjected to little more discomfort. Try to assign money value for all these elements and then aggregate all the elements to get the total. Then compare these two aggregate values which are termed as generalized cost for deciding the choice of destination for making a trip, right. You may wonder how to assign money value for your time. There are methods available. It is possible to assign money value for time of any individual traveler, right. And how do we assign money value for level of comfort? There are methods available to assign money value for level of comfort or discomfort, right. And these theories are discussed in the subject transportation economics in detail. So as of now we can assume that it is possible to assign money value for all these elements and get aggregate money value, and that is how we need to understand travel impedance. It is sum of all the related factors. Now take Wij as the basis and proceed further to model trip distribution. So, we have identified two important factors, the attractiveness of the zones and then the travel impedance defined as Wij, which includes distance, travel time, out of pocket expenditure, related inconvenient discomfort all together, right. And the model that is used to theoretically explain trip distribution is named as gravity model. This model is based on the Newton's law of gravitation. The gravity model, as indicated here, gets its name from the fact that it is conceptually based on Newton's law of gravitation, which states that the force of attraction between two bodies in space in general is directly proportional to the product of the masses of the two bodies and inversely proportional to the square of the distance between them. This is the very well known Newton's law of gravitation. Now, the question before us is how to use this theoretical concept to explain trip distribution. It is concerned with two bodies in space separated by some distance. Once you know the masses of two bodies and the distance between them, you will be able to quantify the attractiveness between the two bodies. How to apply this principle in understanding distribution of trips? Consider two traffic zones as two bodies, right, zones I and j, right, and the spatial separation between the two zones will be known to us because we know we are fixing zone centroids, we know the spatial separation. So, distance between the two zones are also known, right, and then how to define the mass of the zones. Attractiveness of the zones. Let us say one zone is production zone, another zone is attraction zone, or mix of production and attraction. In that case, it is both the extent of production as well as attraction, Pi and Aj, right. That is how you must understand the mass of zones. It could be the quantum of production or mix of production and attraction, in another case quantum of attraction or mix of both. Okay. Total trip ends associated with the traffic zones can be considered as the mass associated with the traffic zones, right. Then you can apply this law, provided we accept this law can be applied for understanding trip distribution. Can we accept this law? Because we have already agreed that the trip interchanges are directly proportional to more or less the attractiveness of the traffic zones. So, that concept can be incorporated very clearly here, and the spatial intervening factors, spatial separation expressed as travel impedance, is not it. So, it is possible to apply this principle to understand trip distribution. That is, Newton's law can be written like this: force of attraction between the two bodies can be written like an equation using a proportionality constant k as F to be equal to k into m1 m2 divided by r squared. m1 m2 are the masses of the two bodies and r is the distance between the two bodies, and the square of the distance is the denominator, and k is the proportionality constant, right. And variations of this formula have been applied to many situations involving human interactions also, about which we are not going to discuss in detail, but just for information. It is not that this law is confined to a particular aspect, it is a very general principle applied for different situations to explain and understand the effect of attractiveness. It could be between individuals also, right. The application of this concept to trip distribution takes the form as given here. You can say instead of force, the total number of trips interchanged between I and j is equal to k times pi aj divided by wij raised to power c. We have just generalized the exponent part. Instead of 2, we are just giving a notation c. So, m1 and m2 are represented as simply pi and aj, and f is understood here as total number of trip interchanges between this particular zonal pair, between zones I and j, is not it? That is how we can understand the force, total number of trips interchange between a given zonal pair of zones taken at a time, right. And trip productions and attractions of the zones replacing the masses of the bodies, and the travel impedance between zones taking the place of r. That is what we have done. We have just substituted Pa and Aj for m1 and m2, and r squared is replaced by Wij raised to power c. The exponent of the impedance term, the denominator, however, does not need to be exactly equal to 2 as I said, but may be replaced by a model parameter c. That is what we have done. Clear? And let us hold at this point and just try to recapitulate what we did so far in this class. We started our discussion with the understanding that on completion of mode choice analysis, we were able to quantify the association of modes related to the trip ends at the zonal level. That is how we just saw the trip ends with different colors indicating different modes in the choice process at the zonal level. Then we discussed about presentation of the data available for analyzing trip distribution in the form of PA matrix and OD matrix, right. In fact, we can first present the data in the form of PA matrix and then convert PA matrix into OD matrix for the purpose of applying the information for the last step, namely traffic assignment. Now we are very clear about the procedure of converting PA matrix into OD matrix. Then we try to understand the factors that might influence distribution of trips between traffic zones. We are now clear that the quantum of trip production and attraction and the spatial separation between the zones expressed in the form of generalized cost of travel are the factors that will influence trip distribution between zones. And to provide a mathematical formulation for these factors to be put into a formula, we found that Newton's law of gravitation could be a good basis, and we have also substituted the variables involved in the Newton's law of gravitation with the variable that we know in the form of production, attraction and travel impedance, and we are able to now formulate an equation to explain distribution of trips between zonal pairs. We will stop here and continue our discussion in the next class.